Good evening, scholars. Mr. Spears here. In tonight's lesson, we're learning about single replacement reactions. You recall from a previous lesson about types of chemical reactions that single replacement reactions are reactions where an element replaces another element within a compound. We can see here in this generic equation that element A replaces element B in the compound BC. As a result, B is now an element by itself, and A has replaced it in the compound with C. Single replacement reactions are the chemical equivalent to a very socially awkward situation. In this cartoon, we see that this very happy couple has their relationship interrupted by a beautiful stranger. As you can see here, the girl in the pink dress is replaced by the attractive stranger. The now ex-girlfriend finds herself alone on the sidewalk, while our proverbial player has a new girl at his side. In this illustration, the couples represent a compound. The attractive woman represents an element who attempts to replace another element within the compound. As is the case with all single replacement reactions, you start off with an element and a compound, and after the reaction is complete and one element is replaced, you also end up with an element and a compound. Now, to aid us later when we're writing balanced chemical equations of these types of reactions, let's review a few characteristics of single replacement reactions. First off, the compound in these reactions is usually an aqueous ionic or acid molecule. Also, metal elements replace cations in the compound, whereas nonmetal elements replace the anions in those compounds. Another important detail to note is that all would-be single replacement reactions don't always take place. Pairings react according to the activity series, which is basically a list to help chemists and students know if single replacement reactions will take place or not. So I want to take a little time reviewing this list and how it works. Basically, an element can replace any element below it on the activity series, none above it. So I'm going to run through 3 examples so you see how this list works. In our first example, solid magnesium is mixed with an aqueous solution of copper 2 chloride. Now, copper 2 chloride is an ionic compound. The charge of copper is 2 positive and the charge of chloride is 1 negative. Remember that magnesium is a metal from the periodic table, and metal atoms try to replace cations in these types of reactions. So the magnesium is going to try to replace the copper. Now, this reaction will only work if magnesium is higher on the activity series list than copper. So we go to the activity series for metals and we note the positions of magnesium and copper. Notice that magnesium is higher on the activity series than copper. Therefore, magnesium is more reactive and will replace copper in this compound with chloride. So this reaction will take place. In our next example, we have an aqueous solution of sodium fluoride mixed with chlorine gas. Sodium fluoride is an ionic compound. The charge of sodium in this compound is 1 positive, fluoride 1 negative. The element in this reaction is chlorine. This is a nonmetal. Remember that nonmetals will replace anions in these types of reactions. So chlorine is trying to push out fluorine and bond with sodium. Again, to know if this reaction will take place, we must look at the activity series for fluorine and chlorine. Fluorine and chlorine are elements from a group on the periodic table known as the halogens. Halogens also have an activity series, and we read this activity series the same as we did for the metals. So we note the positions of chlorine and fluorine on this list. We notice that chlorine is below fluorine on its activity series. Thus, fluorine is more reactive, and chlorine does not have the ability to replace it in the compound with sodium. So this reaction will not work. Finally, we take a look at the would-be reaction between solid zinc and water. When water ionizes, hydrogen has a 1 positive charge, and of course oxygen would have a negative charge. Zinc, being a metal, will try to replace hydrogen in the compound with oxygen. Now, when we look at the activity series and we find zinc, we see a special note about zinc and other elements on this list and their ability to replace hydrogen in single replacement reactions. Zinc is able to replace hydrogen, but only the acidic hydrogens of acids. Zinc cannot replace hydrogen in water. Elements such as lithium, rubidium, potassium, barium, calcium, and sodium, they can replace hydrogen not only in acids but also in water as well. So because zinc can only replace hydrogen in acids and not water, this reaction will not work. Now, one final note about the activity series. There are other factors that play a part in this list, but one cannot overlook the role that ionization energy plays in the development of this list. Generally speaking, metals that have lower ionization energy tend to be more reactive than metals that have higher ionization energy. And this is simply because metals like lithium do not hold onto their valence electrons as tightly, and it's a lot easier for nonmetals like fluorine and oxygen to take their valence electrons from them. Therefore, they are preferred over metals with higher ionization energies, which tend to be a little bit more stingier and hold on to their valence electrons tighter. For nonmetals, such as the halogens, nonmetals higher in electronegativity tend to be more reactive than nonmetals with lower electronegativity. electronegativities. And this is simply because nonmetals with high electronegativity do a much better job of attracting and pulling away electrons in bonds than do elements like iodine that are lower in electronegativity. And if you were a metal and you're trying to get rid of your valence electrons, a nonmetal higher in electronegativity would be preferred over one that has a harder time taking your electrons. Now I want to show you how to write balanced chemical equations for single replacement reactions. If the reactions don't work according to the activity series, we're going to write no reaction. First off, I want to draw the attention to the student that in single replacement reactions, we are always reacting an element with a compound, and we expect to get an element and a compound as products. So looking at lithium bromide and examining its charges, we see that lithium has a 1 positive charge and bromide has a 1 negative charge according to the periodic table. Fluorine is a nonmetal, and as a nonmetal, it will try to replace the anion bromide in the compound with lithium. To see if this reaction will take place, we look at the activity series for halogens, and we notice the positions of fluorine and bromine. Fluorine is higher on the list than bromine, thus this reaction will take place, and fluorine will replace bromine and will form a new compound with lithium. Remember to pay attention to the charges of the ions to make sure that you have the new compound's formula written correctly. Lithium has a positive charge, fluorine a negative charge, and so LiF is the correct formula. And remember, bromine is a diatomic element when it's by itself, and so we write Br2. We want to make sure that these equations are balanced, and so a coefficient in front of the lithium bromide and a coefficient in front of the lithium fluoride will balance our equation. In our next example, we notice a reaction that we actually did as a demonstration earlier in the school year, and that is mixing solid sodium with water. Now, a suggestion to the student is for replacement reactions, whether they be double or single replacement, a student might find that these reactions are written easier when water is written as HOH as opposed to H2O. Now, since water is the compound here, we examine the charges. Hydrogen, positive 1, hydroxide, 1 negative, and sodium being a metal will try to replace the positive cation in water. In other words, the hydrogen at the beginning. Before we write the products, we need to know if this reaction will work or not. And so we go to the activity series and we find the location of sodium, and we read that sodium will replace hydrogen in both acids and water. So this reaction will work, and sodium will replace hydrogen or bump it out, and hydrogen by itself is H2, and sodium will now be in a compound with hydroxide or OH. The ionic charge of sodium is 1 positive, of hydroxide is 1 negative. These charges cancel out, so the formula of sodium hydroxide is NaOH. We have our formulas written correctly, and so now we need to make sure that the equation is balanced. We note 1 sodium on the left and 1 sodium on the right, 1 hydroxide on the left, 1 on the right, but we have this 1 hydrogen at the front of water, and on the right side we have 2 hydrogens. So we need to get 2 waters on the left side to account for this extra hydrogen. Notice that when we add the coefficient of 2 to double up our hydrogens in the beginning, that also doubles up the amount of hydroxide. And so now we need to get 2 hydroxides on the right side. So I add a coefficient of 2, and that also doubles up the sodium on that side. So I need to go back to the left side and add a coefficient of 2 so I can get 2 sodiums on that side. Therefore, our balanced chemical equation becomes 2 sodium atoms plus 2 water molecules yields hydrogen gas plus 2 sodium hydroxide molecules. In our final example, we have solid chromium, a metal element, mixing with potassium nitrate, and we want to know if this reaction will work so we can write the balanced chemical equation. We examine the compound potassium nitrate. We notice that potassium has a positive 1 charge and the nitrate has a 1 negative charge. The metal chromium will try to replace the positive potassium in the compound with nitrate. So to find out if this reaction will work or not, we have to locate these elements on the activity series. We notice that chromium is lower on the activity series than potassium, which means it's not as reactive to be preferred over potassium in the compound with nitrate. In other words, it's a lot easier to take electrons from potassium from nitrate's perspective than it is from chromium. So nitrate is going to prefer to stay with the potassium. So chromium is not reactive enough and therefore will not react with potassium nitrate. So for this combination, there is no reaction. Alright, that does it for tonight's lesson. I hope this helped. If you have any questions, send a message to my YouTube channel. And for my students, write down any questions you may have and bring them to class. Thanks for watching and have a great day.